Welcome to the Deep Dive, the show where we unpack groundbreaking research and make it instantly relevant for you. Today, we're diving deep into one of the most persistent and, frankly, perplexing challenges in artificial intelligence: true, deliberate reasoning. We've all seen the incredible, almost magical abilities of large language models, right? They can generate stunning prose, summarize vast amounts of information, even write functional code. Yet, when faced with problems that demand deep, step-by-step logical thought like a truly difficult Sudoku puzzle or navigating a complex, winding maze, they often stumble. It feels like they're just guessing, or relying on explicit instructions rather than internal, robust computation. Our mission today is to explore a new research paper titled Hierarchical Reasoning Model, or HRM. This paper proposes a truly radical solution to this very problem. We're going to break down HRM, a model directly inspired by the fundamental architecture of the human brain. And you're going to hear about its genuinely surprising performance on tasks where even today's most advanced AI systems completely fall short. Here's the big idea, the aha
moment that sets the stage for our deep dive. What if AI could think with both fast and slow systems, much like our own brains? What if it could achieve near-perfect accuracy on these incredibly complex reasoning tasks with an astoundingly small footprint? We're talking just 27 million parameters and a mere 1,000 training examples per task, all without any pre-training and without relying on the typical crutch of chain-of-thought reasoning that so many LLMs depend on. We're going to show you how HRM is achieving exactly that, even outperforming much larger models on key benchmarks considered crucial for artificial general intelligence. Every fascinating detail, every surprising fact we uncovered today comes straight from this groundbreaking work by Guan, Wang, and colleagues from Sapient Intelligence and their affiliated institutions.
Yeah, and the paper immediately gets right to the heart of why current AI, particularly large language models, struggles with genuine reasoning. It highlights a paradox. Despite deep learning being designed, to add more layers for greater representational power and improved performance, the core architecture of many LLMs is, ironically, quite shallow.
Shallow. Okay, let's unpack this. It's like building a skyscraper that's incredibly wide,
Yeah.
but only a few stories tall when it comes to fundamental reasoning.
That's a great analogy. They're vast in knowledge, perhaps, but their core reasoning process, the number of sequential computational steps they can effectively perform, is surprisingly limited. The paper explains that this fixed, shallow depth imposes fundamental constraints on their reasoning abilities. It essentially limits them to certain computational complexity classes like AC0 or TC0, which are, well, quite restrictive.
So they can't handle problems needing many steps, needing that polynomial time computation.
Exactly. This fixed, shallow depth means that LLMs, when used in their pure end-to-end manner, simply cannot execute the complex algorithmic reasoning needed for deliberate planning or, say, symbolic manipulation tasks. They aren't Turing-complete in that fundamental sense. They lack the ability to perform arbitrary, multi-step computation like a general-purpose computer can.
No.
And the paper provides a very clear example with Sudoku. They found that merely increasing a transformer's depth or width doesn't get it to optimal performance. It quickly hits a saturation point. Performance just stops improving.
So it's not just a scaling issue.
Right. It strongly suggests a fundamental architectural limitation, not just a case of needing more data or bigger models of the same type.
So just throwing more computational power or more data at a fundamentally limited design isn't going to magically make it think better or more deeply. And that brings us to something that's become absolutely ubiquitous in the world of LLMs, chain of thought, or Cote. This is how LLMs have largely attempted to simulate complex reasoning, right?
Indeed. Coden works by externalizing the reasoning process into token-level language. It effectively breaks down complex tasks into simpler, intermediate steps, generating these steps sequentially as text.
So it writes out its thinking process.
Pretty much. So while it helps LLMs arrive at correct answers by providing a step-by-step textual trace, it's a method for them to simulate reasoning. It's not performing true internal deep computation within its latent space.
And the paper doesn't mince words here. It argues that while Conan has been an incredibly valuable tool, a huge step forward for LLMs, no doubt, it's ultimately a crutch, not a satisfactory or long-term solution for true general intelligence. Why is that? What are the big limitations?
Well, the paper really details why Conan is considered a crutch. First, it's remarkably brittle.
Brittle? How so?
Conator relies heavily on breaking tasks down into sequences that are often implicitly or explicitly defined by humans or derived from human-generated examples. If there's a single misstep, a logical error in one of those sequential steps, or even just a misordering, the entire reasoning process can derail completely.
like following a very precise recipe, and one typo ruins the whole dish.
Exactly that. It lacks the robustness of genuine internal reasoning where you might catch an error and backtrack internally.
That makes perfect sense. It's not flexible enough to self-correct in the same way a human might.
Precisely. Second, Cody is fundamentally tethered to language. The reasoning process is tied to token-level patterns and generating text. The paper argues this isn't how the brain fundamentally works. Our brains don't constantly translate every thought, every sub-step of a complex computation into internal sentences.
Right, language is how we communicate thought, not the thought itself.
Exactly. Language is a powerful tool for human communication and expressing thought, but it's not the primary substrate of thought itself. Third, it's data-intensive. It demands significant amounts of training data, often in the form of step-by-step demonstrations, which really works against the goal of efficiency and low resource usage.
More data,
And finally, it's often slow and resource-heavy. Generating a large number of tokens for complex reasoning tasks, especially when simulating deep computation, leads to slow response times and high computational costs.
This next part really makes you think about how our brains operate. The paper points out that language is a tool for human communication, not the fundamental substrate of thought itself. Our brains reason incredibly efficiently in a latent space, an internal, non-linguistic representation, without constantly translating back to language. This desire for what the paper calls latent reasoning seems to be the core idea behind finding a better, more efficient way for AI to think. But if traditional deep models struggle with true depth, how do you even begin to achieve that kind of efficient internal latent reasoning?
That's the core challenge, yeah. The challenge with latent reasoning in traditional deep models is significant, as the paper explains. Even when models aim to perform computations within their internal hidden state space, naively stacking layers to achieve greater effective depth is notoriously difficult.
Why is that?
It's largely due to the pervasive problem of vanishing gradients. The signals needed for learning effectively disappear. They get weaker and weaker as they propagate back through many layers.
Yeah, so the deeper layers just don't learn properly.
Right. This severely hinders training stability and effectiveness, making it hard for information to propagate and for the model to truly learn deep, complex functions. Now, recurrent networks, RNNs, are a natural alternative for sequential tasks and can theoretically achieve arbitrary depth.
Okay, so why aren't they the answer?
Well, they suffer from their own problems, notably early convergence.
Early convergence.
Yeah, it means their hidden states tend to settle into fixed points too quickly. They stop changing. This renders subsequent computational steps kind of inert. It effectively caps their actual useful depth. They stop thinking too soon.
Okay.
Furthermore, training these recurrent networks typically relies on backpropagation through time, or BPTT.
Right, you mentioned that earlier, expensive and memory hungry.
Exactly. BPTT is both computationally expensive and memory-intensive, as it requires storing all hidden states from the forward pass for gradient calculation. And critically, the paper also notes BPTT is biologically implausible. The brain doesn't seem to replay its entire history to learn or assign credit to past actions.
It probably uses more local real-time mechanisms.
That's the thinking, yes. More efficient local updates.
So if current AI architectures are fundamentally limited, and even the popular fixes like Code-T have serious drawbacks, where do we look for a breakthrough? The paper makes a powerful argument. We should look to the ultimate deep reasoner, the one that's been solving complex problems for millennia, the human brain.
Yes, the human brain provides an incredibly compelling blueprint for achieving the effective computational depth that contemporary artificial models lack. The paper emphasizes that the brain organizes computation hierarchically across various cortical regions, and crucially, these regions operate at vastly different timescales.
Different speeds for different parts of the brain.
Sort of, yes. Different processing rhythms. This multi-timescale processing is what enables our brains to perform deep, multi-stage reasoning, from high-level strategic planning down to rapid, detailed execution.
And the paper distills this biological genius into 3 fundamental principles of neural computation that directly inspire the hierarchical reasoning model. What are these guiding principles?
Okay, the first principle is hierarchical processing. The brain integrates information across a hierarchy of cortical areas. This means higher-level areas, like the prefrontal cortex, are responsible for forming abstract strategic representations that unfold over longer timescales. They guide overall goals and plans. In stark contrast, lower-level areas handle rapid, detailed sensory and motor processing, executing the fine-grained steps needed to achieve those higher-level goals.
So it's like a strategic commander brain region setting the high-level objectives, and then highly specialized tactical brain regions handling the rapid, moment-to-moment execution and data processing. Makes sense.
Precisely. The second principle is temporal separation. These hierarchical levels in the brain don't just exist structurally. They operate at distinct intrinsic timescales.
The different speeds you mentioned.
Exactly. This is beautifully reflected in the brain's neural rhythms, like the slower theta waves operating at maybe 4-8 hertz associated with memory and navigation, and the much quicker gamma waves at 30-100 hertz, which are linked to active processing and attention.
Wow.
This temporal separation is key to how our brains manage complex tasks, a slow, strategic process guiding and coordinating a fast, detailed execution. This separation allows for stable, high-level guidance over rapid, low-level computations without them interfering with each other.
That's fascinating. It's like the brain has multiple clocks or internal processing speeds running simultaneously for different types of thought. What's the third principle?
And the third principle is recurrent connectivity. The brain features extensive recurrent connections feedback loops that allow information to flow back and forth, both between different areas and within the same area. These connections enable the iterative refinement of internal representations, allowing the brain to continuously fine-tune its understanding and decision-making.
Kind of like thinking something over, refining the idea.
Exactly. And crucially, the brain largely avoids the deep credit assignment problem that typically plagues artificial recurrent networks that use BPTT, that memory-intensive training method. This suggests the brain has more efficient, biologically plausible ways to learn and attribute success or failure, likely more local.
So armed with these three profound biological insights, hierarchical processing, temporal separation, and efficient recurrent connectivity, the researchers developed HRM. How did these fundamental principles translate into the actual architecture of this new AI model?
Well, inspired directly by this biological architecture, HRM features two tightly coupled recurrent modules. These are designed explicitly to significantly increase effective computational depth in an AI model. First, there's a high-level H module. This is responsible for abstract, deliberate reasoning, directly analogous to those higher-order cortical areas like the prefrontal cortex.
The strategic planner.
Right. And then there's a low-level L module for fast, detailed computations, similar to the rapid, granular processing found in lower-level brain regions.
The detailed executor. Okay, let's really deconstruct the hierarchical reasoning model now. What are the core components that make up this dual-module design? The paper identifies 4 main pillars that interact dynamically, right?
That's right. The architecture consists of 4 learnable components that facilitate this hierarchical interaction. First, you've got the input network, FI. Its primary role is to take the raw input, like a Sudoku grid, and transform it into a meaningful embedded representation that the rest of the model can actively process. Think of it as the initial data preprocessor.
So it's the model's eyes, getting the problem into a format it can understand. Makes sense. What's next?
Exactly. Second, we have the low-level recurrent module, FL. This module updates its hidden state rapidly and frequently within a given cycle. Its computations are conditioned on its own past state, the current abstract state of the high-level module, and the processed input. This module is the workhorse, handling the fine-grained, quick, iterative computations required for detailed problem solving.
Okay, the fast worker, then the high-level one.
Third, there's the high-level recurrent module, FH. This module operates on a much slower timescale, updating its state only once per high-level cycle. It takes in the final output or state of the low-level module from its rapid computations and performs its single abstract update.
So it waits for the detailed work to finish before making a strategic adjustment.
Precisely. This is where the overall strategic planning, the high-level guidance, and the more deliberate thought processes truly happen.
And the final piece, how does it give an answer?
The fourth component is the output network, FO. After the entire hierarchical computation process is complete, this network extracts the final prediction from the high-level module's hidden state. It converts the model's internal representation back into a usable answer or solution, like the solved Sudoku grid.
So what does this all mean for how a model actually thinks or progresses through a problem? How do these two modules, the H module and the L module, actually dance together to solve a problem with this hierarchical dynamic? It sounds quite intricate.
The paper describes a truly elegant and dynamic interaction, really echoing the brain's multi-timescale processing. Imagine an entire computational pass of the HRM as a sequence of n high-level cycles. And within each of these high-level cycles, there are T's rapid, low-level time steps.
Yeah, and slow cycles, T-fast steps within each.
Right. So within each high-level cycle, the L module performs its many rapid computations for its fixed number of 2 time steps. It's diligently churning through the detailed work, following the current high-level strategy set by H. Then, and this is crucial, once the L module has completed its T rapid steps, the H module takes in the L module's final state from that completed phase. Based on this, it performs a single, more abstract update to its own state, refining the overall strategy or abstract understanding.
Oh.
Immediately after the H module updates, the L module is effectively reset. It then begins a completely new computational phase. But now, critically, within a fresh, updated context provided by the newly updated H module.
So the H module guides the L module's next round of work.
Exactly. This entire process, L module rapid computation, H module update, L module reset, repeats for n high-level cycles until a solution is converged upon or the model decides to halt.
So what does this all mean? It's genuinely like a strategic general, the H module, giving high-level commands and setting the direction, to a specialized tactical unit, the L module. The tactical unit then executes those commands in detail, reports back its findings.
Right.
And based on that report, the general adjusts the grand strategy for the next phase of the operation. That's incredibly clever. It seems like it builds in effective depth by design without suffering from the traditional problems.
That analogy captures it perfectly. And this hierarchical design directly addresses a major problem we talked about in standard recurrent neural networks: early convergence.
Right, where they just stop thinking effectively.
Exactly. Traditional RNNs tend to converge too quickly. Their hidden states settle into fixed points that don't change much. This effectively stalls computation, severely limiting their effective depth and preventing them from performing the long, intricate reasoning chains required for complex tasks.
That's a problem we discussed. They run out of thought or computational dynamism too soon. How does HRM's hierarchical design specifically get around that limitation?
HRM's innovation is what the paper calls hierarchical convergence. Instead of stalling, the L module within HRM converges to a local equilibrium during its rapid T-time step cycle.
A local equilibrium.
Yeah, but here's the key. This local equilibrium is not a dead end. It's dynamically dependent on the high-level state provided by the H module during that specific cycle. So when the H module updates its state based on the L module's final output, it essentially restarts the L module's computational path for the next cycle.
It kicks it back into gear with a new goal.
Precisely. It restarts the L module toward a different, potentially more refined local equilibrium, always driven by the updated abstract strategy from the H module.
So it's not just converging to a dead end, but to a useful stopping point that then feeds into the next higher level, more strategic step. That's a significant difference from traditional RNNs.
It truly is. And if you examine Figure 3 in the paper, you can visualize this clear difference in hidden state activity. HRM's H module shows this steady, gradual convergence over many steps, reflecting its long-term planning and stable strategic updates. The L module, however, repeatedly converges within its rapid cycles before being reset by the H module. You see these characteristic residual spikes in activity right after each reset.
Okay, I can picture that. Peaks and valleys for L, steady decline for H.
Kind of, yeah. It's a stark contrast to standard RNNs, which show rapid decaying activity and quick convergence to basically nothing, or deep feed-forward networks that suffer from vanishing gradients, where activity is mostly at the input and output layers. The outcome, as Figure 2 illustrates regarding the necessity of depth, is that HRM maintains high computational activity over many steps and achieves stable, effective convergence. This directly translates to significantly better performance at any given computational depth. It genuinely overcomes that fundamental limitation of standard architectures saturating performance despite increased depth.
That stability and ability to effectively utilize depth sounds like a major step forward. But we also discuss how training these deep recurrent models usually relies on BPPT, backpropagation through time. You said it has huge memory costs and isn't considered biologically plausible. How does HRM train its deep recurrent architecture without those issues? That seems like a big hurdle.
It is, and the paper addresses exactly that. How do you train such a deep recurrent model without the standard memory-hungry methods? The ingenuity here lies in the approximate gradient approach HRM employs. BPTT, as you rightly noted, requires storing all hidden states from the forward pass. This leads to a memory cost that scales linearly with the number of time steps, OT. This heavy memory burden severely limits batch sizes and GPU utilization, making it impractical for very deep computations.
And the brain doesn't do that anyway.
Right. The human brain doesn't store and replay its entire history to learn, and neither does HRM. HRM avoids BPTT by using a clever one-step gradient approximation. Instead of unrolling the entire computational history through time, it computes the gradient based on only the last state of each module within a cycle. It effectively treats all prior states within that cycle as constant for the purpose of backpropagation.
So it only looks back one step for the gradient.
Essentially, yes. The gradient path becomes a much shorter, more local chain. From the output head back to the final H module state, then to the final L module state, and finally back to the input embedding. It doesn't need to remember everything in between.
So it maintains a constant memory footprint, regardless of how many computational steps it takes. That's a huge efficiency gain.
Exactly. This results in an O1 memory footprint. Constant memory, no matter how long it thinks. There's no unrolling through time, which makes it incredibly scalable and critically more biologically plausible. The paper explains that this aligns with the idea that the brain might perform credit assignment via short-range, local mechanisms rather than needing to replay its entire activity history.
Okay.
This approach has theoretical grounding in concepts from deep equilibrium models, or DEQs, which leverage the implicit function theorem to bypass BPTT, but the core idea is that efficient approximation.
So efficiency and biological plausibility built right into the training. That's a huge step forward. What else does HRM do to enhance its learning process and ensure robust training? Any other tricks?
Another key element is deep supervision. This concept is also inspired by a biological principle. The idea that periodic neural oscillations in the brain might regulate when and how learning actually occurs.
Like rhythms for learning.
Something like that. In HRM, deep supervision means that for each data sample, the model runs multiple forward passes. They call these segments of computation. After each segment, a loss is computed based on the current prediction, and the model's parameters are updated.
So it's getting feedback more frequently throughout the learning process, almost like having continuous checkpoints instead of just one grade at the very end.
That's a great way to think about it. And the crucial detail here is that the hidden state from one segment is detached before being used as the input state for the next segment.
Detached.
Yeah, it means the gradients don't flow back from one segment into the previous one. This prevents gradients from propagating too far back across the entire sequence of segments. It effectively creates another form of one-step gradient approximation, but this time for the overall training process across segments.
Ah, okay. So more frequent, but still localized learning signals.
Exactly. This frequent feedback, especially to the H module, acts as a powerful regularization mechanism. It leads to superior empirical performance and significantly enhanced stability during learning. It helps the high-level module learn more effectively and robustly.
That's incredibly smart. Speaking of thinking fast and slow, the paper talks about adaptive computational time, or ACT. Is this where the model learns to decide how much to think about a problem like we do?
Yes, ACT is precisely that mechanism. It's directly inspired by how the human brain dynamically adjusts its runtime or effort based on the perceived complexity of a task. You know, like Daniel Kahneman's System 1 for automatic fast thinking and System 2 for deliberate, slow, effortful thinking.
Right, sometimes you just know the answer, other times you have to really work it out.
Exactly. HRM implements this using a Q learning algorithm, a type of reinforcement learning. After each computational segment, a special part of the model called a Q head, it's just a small neural network, predicts Q values for two possible actions. Halt.
Stop thinking, give the answer.
Right. Or continue.
Keep thinking, do another segment.
Precisely, based on the current state of the high-level module.
So it's not just running for a fixed number of steps. It's learning to decide how much thought to put into a problem, just like we might decide to spend more time on a difficult puzzle. That's incredibly elegant and practical.
It truly is. The decision to halt or continue is made dynamically during inference. There's usually a stochastic minimum number of segments, say MN, to encourage some baseline level of deeper thinking.
Makes sense. Don't want it quitting too early on everything.
And a maximum limit, MX, to prevent it from getting stuck in infinite loops. And Figure 5 in the paper clearly illustrates the practical benefits of ACT. It shows how HRM adaptively uses computational resources. It achieves significant savings while maintaining comparable or even superior performance compared to models that just run for a fixed number of steps. It only uses more compute when it actually needs it.
That's huge for efficiency. And it also mentions inference timescaling. What does that mean for the practical application of HRM, especially in real-world scenarios?
Inference timescaling is a really remarkable property. It means that HRM models, once trained with a specific maximum computational limit, let's say MMax, can actually generalize and improve their accuracy when given higher computational limits during inference. That's the key. During inference, when you're using the model without needing any further training.
Wow. So you train it once, but you can make it think harder later if needed.
Exactly. You can deploy the model, and if a particularly difficult problem comes along, you can simply allow it to run for more segments, more computational time, and its accuracy is likely to improve. The paper highlights this by showing that for tasks requiring long-term planning, like that tough Sudoku extreme, additional inference time computation greatly benefits performance. But for tasks like ARC-AGI, which generally require only a few transformations, the gains from extra time are minimal.
Which shows it's truly adaptive. It knows when more thinking will help and when it won't.
Precisely. It demonstrates its genuinely adaptive and resource-efficient nature.
And what about the stability of this Q-learning part? Q-learning, or particularly deep Q-learning, can be notoriously tricky to stabilize in deep networks. How does HRM ensure that component works reliably?
That's a very important technical consideration, yeah. Deep Q-learning is indeed known for its instability, often requiring complex stabilization techniques like experience replay buffers or separate target networks. However, the paper notes that HRM achieves stability primarily through its intrinsic architectural properties and the specific training procedure they use. Specifically, it employs a post-norm architecture with RMS norm. RMS norm is a robust form of layer normalization that helps stabilize activations.
Okay.
And they use the AtomW optimizer. AtomW is known to help keep model parameters bounded and contribute significantly to the stability of the Q-learning process without needing those extra external stabilization mechanisms common in RL.
So it's all baked into the core design, making it robust and efficient. That's impressive engineering. And for those listeners curious about the deeper technical specifications, what kind of architectural specifics does HRM employ under the hood to build these H&L modules and the other networks?
Right, so at a fundamental level, HRM utilizes a sequence-to-sequence architecture.
Meaning it takes a sequence in and outputs a sequence.
Yeah, both input problems like the Sudoku grid and output solutions are represented as sequences of tokens. It converts the input grid into a token sequence, processes it, and then converts the model's output sequence back into a structured answer. Both the low-level FL and high-level FH recurrent modules are implemented using encoder-only transformer blocks.
So you use the transformer components, leveraging that powerful architecture.
Exactly. It leverages the powerful attention mechanisms and representational capabilities of transformers within its recurrent structure. Importantly, these modules, H and L, have identical structures and dimensions, allowing for a consistent computational framework between the levels. The design also incorporates many of the enhancements found in highly successful modern large language model architectures, like the Llama family, such as things like rotary positional encoding or ROP. This helps the model effectively understand the relative and absolute positions of information within a sequence, which is crucial for spatial tasks like Sudoku or maze navigation. It also uses gated linear units, GLUs, and RMS norm, which, as we mentioned, are critical for stabilizing and enhancing the effectiveness of the network's layers during training.
Okay, standard modern LLM best practices.
Pretty much. Additionally, the architects remove bias terms from the linear layers, a technique often used to improve stability and potentially reduce overfitting. And as mentioned, the model uses a post-norm architecture overall, and specifically the AtomAnt2 optimizer, which they found further contribute to stable and effective training across its deep recurrent structure.
So not just a clever high-level design, but also incorporating state-of-the-art components at the lower level.
Exactly. These are not just arbitrary choices, but reflect best practices in modern neural network design, adapted specifically for HRM's unique hierarchical challenge.
Now let's talk about the real-world performance, because this is where HRM truly stands out. The paper talks about incredible efficiency. How much data and what kind of setup did they use to train HRM to achieve these results? This part sounds almost too good to be true.
The training setup is genuinely astonishing, especially when you contrast it with the insatiable data demands of current large language models. HRM models were initialized with random weights. So starting from scratch, No prior knowledge baked in.
No pre-training at all.
None. And they were trained in a simple sequence-to-sequence setup. Crucially, they used only about 1,000 training examples per task.
Hold on, 1,000 examples per task. Like 1,000 Sudoku puzzles.
Yes. Think about that for a moment. 1,000 examples for an AI to master a task like Sudoku Extreme or RC AGI. And again, no pre-training involved, which is standard for almost all high-performing LLMs today, nor did they require any chain of thought labels in the training data.
That is a staggering level of data efficiency. It really signals a potentially paradigm-shifting approach compared to needing billions or trillions of tokens.
It really does.
So what were the battlegrounds for these tests, the key benchmarks where HRM showed its dominance over other models? The paper mentions 3 main ones.
Right. The paper evaluated HRM on 3 key benchmarks, and you can see the comparisons clearly in Figure 6. These benchmarks were specifically chosen because they challenge different facets of complex reasoning abilities. The first is the ARC-AGI challenge, which stands for the Abstraction and Reasoning Corpus.
Right, RRC-AGI. I know this one. It's infamous for being incredibly difficult for AI, often described as an IQ test for machines, needing that kind of fluid intelligence.
Exactly. RC-AGI evaluates general fluid intelligence and inductive reasoning through visual IQ test-like puzzles. The core challenge in RC-AGI 1 is that models must extract and generalize abstract rules from a very small number of examples, typically just 2 or 3 input-output pairs.
Learn the pattern from just a couple of examples.
Yes, and then apply that newly learned rule to a completely novel test input. It's incredibly challenging for conventional deep learning and especially for Kuriti because it truly requires generalizing to entirely new, unseen tasks rather than just interpolating from patterns it's seen thousands of times. And RSC-AGI2, which is a significantly expanded version, emphasizes even deeper compositional reasoning, multi-step logic, and symbolic abstraction.
Things humans are good at, but AI really struggles with.
Exactly. Human calibration shows these tasks are challenging but doable for people, yet they've proven extremely hard for even the most advanced contemporary AI systems.
So on this ultimate intelligence test, how did HRM perform? What were the numbers?
On ARC-AGI2, HRM achieved an accuracy of 40.3%. Now here's where the comparison becomes truly striking. This substantially surpasses leading COTI-based models like O3 Mini High, which is a strong baseline. That managed 34.5% accuracy. And it even beats models like Claude 3.7 with an 8K context window, which only achieved 21.2% on this specific version.
Wow, nearly double Claude's score, with only 27 million parameters.
Exactly. Remember, HRM achieved this with only 27 million parameters and a context length equivalent to just a 30 by 30 grid that's only 900 tokens. A tiny computational footprint compared to these much larger COTI-reliant models. And importantly, the direct pred transformer baseline, same size as HRM, same training data, no hierarchy, no pre-training, performs significantly worse on ARC-AGI1 and failed entirely, 0% on Sudoku and Mace.
So the hierarchy is crucial.
It appears so. HRM more than doubled its performance on ARC-AGI compared to that direct non-hierarchical baseline.
That's truly remarkable. It's not just better, it's significantly better with a mere fraction of the resources and data. What about Sudoku? The paper talks about Sudoku Extreme. I thought Sudoku was basically a solved problem for AI these days.
That's a common misconception, and what's fascinating here is that the paper emphasizes the critical distinction of Sudoku Extreme. While a standard 9x9 Sudoku puzzle unique digits per row, column, and 3x3 block is a classic benchmark for logical reasoning, got common datasets, like those from Kaggle or those minimal 17-clue puzzles, are considered easy by the research community. They can often be solved with relatively elementary techniques or have hints that make the path pretty direct.
Okay, so extreme really means extreme.
It does. Sudoku Extreme is a curated collection compiled from puzzles recognized by the human Sudoku community as exceptionally difficult. These often require advanced human strategies like forced chains or X-wing logic, and crucially, extensive trial and error or backtracking.
The guessing and checking part.
Exactly. The true difficulty is often measured by the number of backtracks or guesses required by a smart algorithmic solver program. Sudoku Extreme averages 22 backtracks per puzzle. That's astronomically higher than other benchmarks like Sudoku Bench, which averages only 0.45 backtracks.
22 versus less than 1. Okay, that's a huge difference.
It really is. This dataset truly demands extensive tree search and backtracking, making it a robust test for deep logical reasoning.
That puts the extreme in perspective. So how did HRM fare against what sounds like the AI's kryptonite for logical reasoning? did it manage?
HRM achieved nearly perfect accuracy on Sudoku Extreme.
Nearly perfect.
Oh,
On puzzles needing 22 backtracks on average.
Yes. And the crucial comparison here is that state-of-the-art Kutsi methods, the very approach LLMs rely on for reasoning, completely failed on this benchmark.
Failed how badly?
0% accuracy.
Zero.
Zero. This task, demanding such deep iterative search and backtracking, proved utterly intractable for even advanced LLMs employing chain of thought. It just highlights HRM's unique capacity for this type of complex, systematic problem solving.
0%. That's a total shutdown for the other models. Just unbelievable. What was the third benchmark that HRM tackled?
The third benchmark was maze hard. This task involves finding the optimal or shortest path in a large 30 by 30 maze. And to ensure its difficulty, the dataset was specifically filtered to include only instances where the shortest path length exceeded 110 steps.
So long, complex paths only.
Exactly. Ensuring that complex multi-step planning was absolutely required. And a path is considered correct only if it is both valid, staying within the maze boundaries, not crossing walls, and truly optimal, meaning it's the absolute shortest possible route.
Finding the shortest path, not just a path. Got it. And how did HRM perform on maze hard, especially compared to other AI models attempting similar pathfinding?
On maze hard, HRM again achieved nearly perfect accuracy.
Again. Wow.
Yeah. And for context, prior research, which is mentioned in the paper, showed that large vanilla transformer models, we're talking 175 million parameters, trained on 1 million examples, achieved accuracy below 20% on similar 30 by 30 maze tasks.
Below 20% for a big transformer, nearly 100% for tiny HRM.
Once again, HRM, with its tiny parameter count and minimal training data, demonstrated vastly superior performance on a task that completely stymies other much larger models. The paper makes it abundantly clear. For tasks demanding lengthy reasoning traces, which these three benchmarks unequivocally do, the performance gap between HRM and the baselines is significant. The baselines almost never manage to solve the tasks, underscoring HRM's unique and effective ability to handle complex, multi-step, deep reasoning problems where other methods simply falter.
Okay, so HRM is clearly crushing these benchmarks, achieving near-perfect scores where other models fail dramatically. But performance is one thing, understanding how it's doing it is another. These AI models are often criticized as black boxes. Did the researchers manage to peek inside HRM to see its reasoning process? What strategies was it actually employing?
They did. And it offers a fascinating glimpse into its internal workings. While a definitive, complete answer to the, what algorithm is it running, question is still an area for future research. The paper began to address model interpretability by analyzing intermediate predictions generated from the H module's hidden state at each high-level time step.
Looking at its thoughts mid-process.
Kind of, yes. This provides a crucial window into the model's evolving thought process, allowing the researchers to infer its strategy.
What did they find when they visualized these intermediate steps for different tasks? Did it reveal specific, identifiable strategies emerging from the model?
Yes. The visualizations, particularly in Figure 7, reveal remarkable emergent task-specific strategies. It wasn't using the same approach for everything.
Okay, like what?
For the maze task, HRM appears to initially explore several potential paths simultaneously, almost like it's hedging its bets, considering multiple options at once. It then progressively eliminates blocked or inefficient routes as it iterates through the cycles.
Pruning the search space.
Exactly. Finally, it constructs a preliminary solution outline, followed by multiple refinement iterations to find the precise shortest path. It's a very dynamic process of exploration, pruning, and refinement.
Fascinating. What about Sudoku? Did it look different?
Very different. For the Sudoku task, the strategy observed strongly resembles a depth-first search approach. The model appears to systematically explore potential solutions by filling in numbers based on the rules. And critically, it demonstrates the ability to backtrack when it hits dead ends or logical inconsistencies.
It backtracks, so it's literally trying things out and reversing course when they don't work, just like a human trying to solve a truly challenging Sudoku. That's incredibly compelling.
That's precisely the visual implication. It tries filling a square, sees it leads to a problem later, and then undoes that move and tries something else.
Amazing. And the ARC tasks, another strategy.
Yes, for the ARC tasks, HRM employs yet another distinct approach. It seems to make incremental adjustments to the board, iteratively improving it until it reaches a solution state that matches the target pattern. Unlike Sudoku, which involved frequent, sometimes deep backtracking, the ARC solution path observed follows a more consistent progression. It looks more similar to a hill climbing optimization, gradually moving towards the correct abstract pattern with fewer reversals.
That's genuinely smart. The key insight here, according to the paper, is that the model shows that it can adapt to different reasoning approaches, likely choosing an effective strategy for each particular task. This isn't just a brute force application of one method. It suggests a truly flexible and intelligent adaptation to the problem at hand, which is a hallmark of general intelligence.
Exactly. It's learning a repertoire of strategies and flexibly applying the most suitable one rather than being confined to a single fixed approach. That adaptability is really key.
This deep dive has continually linked HRM back to the human brain, citing its architecture as a direct inspiration. And the paper goes even further, exploring a deep brain AI connection through something called hierarchical dimensionality. What is that? And why is it important for understanding how the brain, and now maybe HRM, achieve such complex reasoning?
Yeah, this is a really fascinating part. A crucial question the paper explores is how the brain manages to be so flexible and adapt to so many different cognitive demands. How does it handle novelty and complexity? The answer, according to a lot of neuroscience research, often lies in the dimensionality of its internal representations.
Like how many features it can track.
Sort of. A brain region's ability to handle diverse and complex tasks, its functional repertoire, is closely linked to how many independent features or dimensions its neural activity explores simultaneously. Higher-order cortical areas, like the prefrontal cortex, which are responsible for complex reasoning, decision-making, and planning, need to handle a wide variety of tasks and contexts. This demands more flexible, context-dependent processing, which neuroscience suggests correlates with higher-dimensional state-space trajectories in the brain activity.
So, put simply, more dimensions mean more flexibility and more capacity for complex thought or processing, a bigger mental workspace.
Precisely. It allows for richer, more nuanced representations. To quantify this, the paper uses a standard measure from neuroscience called the participation ratio, or PR.
Okay, PR. What does it measure?
Conceptually, a higher PR means the variance in neural activity is distributed more evenly across many dimensions. It indicates a richer, higher dimensional representation that can encode more complex information patterns. Conversely, a lower PR means the variance is concentrated in just a few dimensions, reflecting a more compact, lower dimensional structure, perhaps specialized for a narrower set of functions.
And is this dimensionality hierarchy, higher dimensions and higher brain areas, something that has actually been observed in biological brains? Is there real-world validation for this concept?
Yes, absolutely. Figure 8AB in the paper shows a compelling parallel observed in the mouse cortex. Researchers have found that the participation ratio of the population activity increases monotonically. It goes up consistently as you move computationally from low-level sensory areas up to high-level associative areas in the cortex.
Wow, it's a direct correlation.
It is. The correlation between hierarchical position and effective dimensionality is quite strong, with reported Spearman correlation coefficient of 0.79. This strongly suggests that a hierarchical organization of representational dimensionality is a fundamental organizing principle in biological intelligence.
So the million-dollar question becomes, does HRM, which is inspired by this biological principle of hierarchy, also spontaneously show this hierarchical dimensionality after it learns to solve these complex tasks?
And the results for the trained HRM are, as the paper puts it, a striking parallel to these biological findings. It's really quite remarkable. After HRM is trained on the challenging Sudoku Extreme full dataset, they measured the PR for both modules. Its low-level module, VL, occupies a relatively small subspace with a participation ratio of 30.22. However, the high-level module, ZH, operates in a substantially larger subspace, demonstrating a significantly higher PR of 89.95.
30 versus nearly 90. That's a huge, significant difference, a clear separation.
A very clear quantitative separation in the representational capacity of the two modules, mirroring their intended functional roles.
And what about the adaptive aspect of the brain's dimensionality you mentioned earlier? Does HRM's high-level module's dimensionality also adapt based on task complexity or variety?
It does, which makes the parallel even more compelling. Figure 8C in the paper shows that the dimensionality of the high-level module ZH actually scales up its PR increases as the number of unique tasks or different types of solution trajectories included in the analysis increases.
So it expands its workspace as needed.
Exactly. This indicates an adaptive expansion of its representational capacity as it encounters more diverse problems and learns to generalize across them. In stark contrast, the low-level module's CL dimensionality remains stable regardless of the task diversity.
Wow.
This strongly suggests an emergent separation of representational capacity that perfectly mirrors their functional roles: high-level abstract and flexible, low-level detailed and stable, just like we believe happens in the brain.
That's incredibly powerful evidence that HRM isn't just performing well, but it might be doing it in a way that truly mirrors a fundamental aspect of biological intelligence. But to really prove this isn't just an artifact of the architecture, they must have done a control analysis, right? To show it's something the model learned, not just a feature of having two modules.
Absolutely. That's a crucial scientific step to verify that this hierarchical organization of dimensionality is truly an emergent property that arises from the learning process, and not merely an architectural artifact. The researchers performed a critical control analysis. They tested an identical HRM model, but with random weights essentially, an untrained network processing the exact same task inputs given to the trained model.
Okay, so what did the untrained random network reveal about this hierarchical separation? Did it show the same pattern?
The results, vividly shown in Figure 8, EF, reveal a stark contrast. The untrained network showed no hierarchical separation in dimensionality whatsoever. The participation ratio values for both its low-level ZL and high-level ZH modules remained low and were nearly indistinguishable from each other.
What were the numbers?
The ZL had a PR of 42.09 and ZH had 40.75. Very close, and both relatively low compared to the trained ZH. No significant separation at all.
Okay, that nails it then.
Yes. This validates that the dimensionality hierarchy is indeed an emergent property that arises as the model learns to perform complex reasoning. It's not just a built-in feature of the architecture, it's something the model learns to develop through training on challenging tasks.
That's the clear evidence right there. It emerges through learning, which is a significant finding. And the paper also mentioned something about conventional deep networks often exhibiting neural collapse. What is that phenomenon, and how does HRM differ from it?
Yeah. Right. Neural collapse is an interesting phenomenon observed in many conventional deep networks, especially during classification tasks. It's where, during training, the features or representations in their final layers tend to converge or collapse onto a very low-dimensional subspace. The representations for different classes become very simple and distinct, but lack richness. This effectively limits their representational capacity and flexibility, making them good for specific tasks like classification, but perhaps less suited for complex, generative, or reasoning tasks requiring richer internal states.
So they become too specialized, too simple at the end.
In a way, yes. HRM, however, departs significantly from this pattern. Instead of collapsing, it actively fosters and maintains a high-dimensional representation in its higher-level module, as evidenced by that high PR we saw for the trained ZH. This is profoundly significant because such high-dimensional representations are considered crucial for cognitive flexibility, for handling a wide range of tasks and contexts effectively. They are seen as a hallmark of higher-order brain regions like the prefrontal cortex, which is absolutely central to complex reasoning, planning, and abstract thought in humans.
So HRM is doing the opposite of neural collapse in its reasoning engine.
In its high-level module, yes. So by partitioning its representations into this high-capacity, general-purpose, high-dimensional space, CAH, and a more specialized, detailed, lower-dimensional space, ZAAL, as the paper states, autonomously discovers an organizational principle that is thought to be fundamental for achieving robust and flexible reasoning in biological systems.
That's a truly foundational principle it seems to have captured. It suggests HRM has maybe stumbled upon or learned a core secret to biological intelligence organization. Although I imagine the paper would wisely caution that this evidence is correlational, not necessarily causal at this stage, right? We see the pattern, but proving it causes the good reasoning is harder.
Yes, the paper does include that important and appropriate scientific note. While the evidence is incredibly compelling and highly suggestive, it is correlational at this point. Testing a direct causal link, for example, by experimentally constraining the H module's dimensionality during training to see if it specifically impairs reasoning performance would be complex, but is highlighted as an important question for future research.
Makes sense.
But the parallels uncovered are indeed undeniable and very, very exciting for the field.
So, bringing it all together, where does HRM fit into the broader AI landscape? We've talked about its unique approach and its impressive performance. How does it stack up against other big ideas and fundamental aspirations in AI, especially regarding something like Turing completeness? Can it theoretically compute anything?
This is a crucial area of discussion in the paper, positioning HRM within the larger goals of AI. It states that, much like earlier neural reasoning algorithms such as the universal transformer, HRM is computationally universal when given sufficient memory and time.
Computationally universal meaning it can simulate any Turing machine.
Theoretically, yes. This means it falls into the rare category of AI models that can, in principle, simulate any algorithm, effectively overcoming the fundamental computational limitations of standard fixed-depth transformers that we discussed right at the very beginning of our deep dive. Those models are stuck in those lower complexity classes.
Okay, but universal transformers existed before. What's new here?
Right. Earlier neural algorithm reasoners also aimed for universality, but they often suffered from practical limitations. Things like the premature convergence of their hidden states, which we discussed,
Right, they stopped thinking too soon.
and the memory-intensive nature of BPTT for training. These issues limited their actual effective depth and scalability in practice. HRM advances significantly on this front by resolving both of those key challenges, the convergence issue through hierarchical convergence, and the BPTT issue through the approximate gradient. And by being equipped with adaptive computation through ACT, it can actually be trained effectively on long reasoning processes. It can solve complex puzzles that demand intensive depth-first search and backtracking, which stymied earlier attempts. So this combination brings it, as the paper puts it, closer to practical Turing completeness than previous recurrent or attention-based universal models.
That's a huge claim. Practical Turing completeness. It implies a fundamental shift beyond the current capabilities of most LLMs we interact with daily. How does HRM's approach contrast with the other popular and widely adopted approach for improving reasoning in LLMs, which is combining reinforcement learning with chain of thought?
The paper makes a clear distinction there as well. While reinforcement learning, or RL, is widely adopted for fine-tuning LLMs, especially to follow instructions or generate better COTI traces, recent evidence suggests that RL primarily helps to unlock or refine existing COTI-like capabilities within the LLMs, rather than truly discovering fundamentally new internal reasoning mechanisms. It gets better at simulating thought, perhaps.
Okay, so RL fine-tunes the crutch. It doesn't replace it.
That seems to be the implication. Furthermore, training QT through RL is known for its instability and data inefficiency. It often requires extensive exploration phases and very careful, often complex, hand-designed reward signals to guide the learning process effectively. In contrast, HRM benefits from dense gradient-based supervision via its C2sec training and deep supervision. It gets direct, continuous feedback on its performance at each step or segment, not the sparse, delayed reward signals that typify RL.
So it learns more directly.
Yes, potentially more efficiently and stably. It also operates naturally in a continuous internal state space, which is arguably more biologically plausible. And it avoids the issue that Qt has of allocating sort of uniform computational resources to each token generated, even when the reasoning complexity can vary greatly from one step to the next. ACT handles that dynamically.
Right, some steps are harder than others. Okay, so it's more efficient, more stable, potentially more flexible than RL for COTI. What about other architectural innovations that focus on efficiency in transformers, like linear attention mechanisms? There's been a lot of work there. How does HRM relate to those?
That's a good point. Recurrence has indeed been explored in the context of linear attention as a way to replace the computationally expensive quadratic time and memory complexity of standard transformer attention. Some linear attention variants use RNN-like state updates to effectively retain long-range context without that quadratic memory growth, making them more efficient for long sequences.
So they bring recurrence back for efficiency.
Yes, but the paper emphasizes that simply replacing the attention mechanism doesn't fundamentally change the fact that the underlying transformer is still fixed depth in its core computation path. Those models often still require CO as a compensatory mechanism for deep reasoning tasks. HRM, conversely, represents a more fundamental architectural shift. It's designed for the nature of deep reasoning itself, incorporating hierarchy and recurrence for depth, rather than just optimizing attention efficiency within an inherently shallow paradigm.
Got it. It's a deeper change, not just an efficiency bolt-on. And finally, the paper briefly touches on related work in brain-inspired AI and hierarchical memory models. What's the quick takeaway there that puts HRM's contribution into perspective against that backdrop?
Sure. There's definitely a rich history of algorithm learning in AI, going back to models like neural Turing machines and differentiable neural computers, which tried to mimic computational hardware components like memory access. And in the more explicitly brain-inspired AI space, models like Spawn or the Tolman-Eifenbaum machine have attempted to create broader cognitive architectures based on neuroscience principles.
But how is HRM different?
The paper highlights HRM's unique advantage. It demonstrates the ability to solve genuinely complex reasoning tasks like Sudoku Extreme, ARC-AGI-2, and Maze Hard, without requiring extensive pre-training or needing any task-specific manual design or hard coding of algorithms. This seems to be a significant leap beyond many of these earlier models, which were often restricted to simpler problems or required more manual intervention and prior knowledge built in. There are also related hierarchical memory models, like hierarchical sequential models or clockwork RNNs, which also use multiple recurrent modules operating at varying timescales.
Sounds similar.
Structurally, yes, but their primary focus has typically been on mitigating the problem of catastrophic forgetting in RNNs over very long sequences. HRM's focus, driven by the brain principles, is fundamentally on enabling deep multi-stage reasoning itself, not just memory retention. It's a different goal achieved through related means.
This has been a truly eye-opening deep dive into what feels like a potentially very different future for AI reasoning. Let's try to recap the core message of the hierarchical reasoning model for everyone.
Okay, so we've seen how HRM, a genuinely brain-inspired architecture, lodges hierarchical structure and multi-timescale processing those slow and fast modules to achieve significant effective computational depth. Crucially, it manages to do this without sacrificing training stability, using approximate gradients or efficiency, using constant memory. And the results speak for themselves. With only 27 million parameters and training on a remarkably small dataset of just about 1,000 examples per task, HRM effectively solves challenging reasoning problems. Problems like the ARC-AGI challenge, the exceptionally difficult Sudoku Extreme, and complex maze navigation. These are exactly the kinds of tasks that typically pose overwhelming difficulties for even today's largest and most capable large language models relying on chain of thought.
Yeah, the performance gap on those hard tasks was just immense. The paper truly challenges the prevailing AI paradigm that has largely favored non-hierarchical models, often relying on massive scale and kind of the main path forward. HRM suggests a viable, powerful, and incredibly data-efficient alternative to these dominant chain-of-thought methods. It seems to propel us towards a foundational framework that's capable of truly Turing-complete universal computation, moving AI beyond just sophisticated pattern recognition and maybe into genuine adaptive problem-solving. This deep dive really reveals that sometimes the most profound path forward in AI isn't simply about scaling up what we already have, just making models bigger and bigger and feeding them more data. Instead, it might be about fundamentally rethinking how our intelligence systems are structured, looking perhaps to the elegance and efficiency of biological intelligence for crucial inspiration. If adopting a brain-inspired hierarchical approach like HRM can unlock such profound reasoning capabilities with so little data and so few parameters, what does this imply for the future of truly intelligent machines? How will they learn, adapt, and maybe eventually help us solve the world's most complex problems? And perhaps more personally, a thought to leave you with. What kinds of hierarchical structures might you start to see in the world around you now? Maybe even in your own thinking processes. Now that you know how powerfully hierarchy, combined with different processing speeds, can enable intelligent, flexible, and deep reasoning,